All right, so last time we saw with strong nucleophiles or base catalyzed epoxide ring openings, we can also do acid catalyzed epoxide ring openings. So we saw this last semester, although we didn't quite give you the whole truth of it. So let's go ahead and take a look at it now. So we've got our alkene, we add some MCPBA. We form our epoxide. And then what we can do here is just add H3O plus. To get our diol, right? Note that they've added an anti-fashion, and of course you get both enantiomers of the product. Let's go take a look at the mechanism of this. So the first thing that happens is this epoxide attacks our H+, which is acting as a catalyst. So it will be regenerated. Of course, we can classify this whole reaction right here as a simple proton transfer, right? We're just transferring a proton. And then after that, we have our molecule of water acting as our nucleophile. And then what we're doing here is essentially an SN2-like reaction. To get to our final product, and then there's another proton transfer to get rid of the excess H+. So we don't just have to use H3O+, we can use other acids as well. So for example, you can use HX, where X is just, of course, your halogen. To add that across there. Or you could add a little bit of acid and some alcohol. To form an alcohol and an ether. In terms of the stereochemistry, it's always going to be an anti-addition, right? No matter what, these epoxide ring openings are always anti-additions. The regiochemistry is a little bit more complicated. And we have kind of two options here, right? So we have our ether. And then, for example, we can add HX. And so which position is that X going to add into? Is the X going to add into the less substituted position? Or is the X going to add into the more substituted position, right? Here it's the less, here it's the more. And so the answer to this is actually a little bit more complicated than you may originally think, and it depends on your substrate. So when your substrate, when you're comparing a primary versus a secondary substitute epoxide. So for example, on the left side here, we have a secondary epoxide. And then on the right side, we have a primary epoxide. The X minus, or your nucleophile, is going to attack the primary position. Right, so when it's primary versus secondary, we are going to attack the primary position, right? And that makes sense. This is like an SN2 type of reaction. Where it gets a little bit more complex is when you have a tertiary epoxide. So here we've got tertiary, there's 1, there's 2, there's 3. Here, when we add the X minus, it's actually going to attack at the more substituted position, not the less substituted position. My bad, I should have drawn both of these as already being protonated because they are acid catalyzed. And so here it attacks the tertiary position. And so this is kind of more of like an SN1-like reaction. And so this most likely has something to do with the structure, right? If we think about this positive charge here, we could have this carbon oxygen bond break, and it breaks. So the way it would break would be to form the more stable carbocation. Right, so it'd like to form this tertiary carbocation. So that makes it more electrophilic, and so our nucleophile is more likely to add at that position, but it's still an anti-addition. So this reaction in this case is somewhere between an SN1 and an SN2 reaction. So just to summarize, if you've got a acid catalyzed epoxide ring opening, if you've got primary versus secondary, you're going to attack that primary position. If you've got a tertiary position, you're going to attack that tertiary position.